Next is Elias FALLON. Please, Elias. Elias FALLON is the Vice President for Machine Learning at Qeexo. He leads the machine learning team in building a product to enable any engineer's vision of tinyML products to become reality. Previously, Elias worked in EDI industry at Neolinear and Cadence for more than 20 years, helping to enable the design of custom and analog chips. He was a co-primary investigator of the Majestic project funded by DARPA to investigate the application of machine learning to EDA for analog ICs. Elias graduated from Carnegie Mellon University with a master and bachelor in electrical and computer engineering. Please, Elias, the floor is yours.
Thank you, Danilo. And so I'll be inspired by Jan and use the mental model of kind of what kind of engineering I come from to kind of bring you into how I approach the AutoML kind of space. So like Danilo just said, I'm not a machine learning engineer by training. I'm an electronic design engineer and a design automation engineer, and I wasn't here 2 years ago, unlike most of the speakers so far. So Sang, the CEO of Qeexo, was here, gave a talk 2 years ago at tinyML. It's kind of one of the companies that's been here for a long time, but I just got into the industry 6 months ago. But I was just the other side of silicon for the last 5 years or so and kind of reversed the nouns and the verbs. I was trying to apply machine learning to the design of tiny electronics and specifically analog chips and things that were very close to sensors. So STMicroelectronics was one of my big customers I worked with all the time. And in terms of trying to work with stuff like that. And so it was a lot of fun. I kind of got hooked by the machine learning thing and decided to go to just the other side. And one of the things that's really always a lot of fun on the electronic design automation side is you're dealing with kind of these enormously huge design spaces, right? You've got too many possible variables. If you wanted to explore all of them, you'd be looking for, you'd be trying out all the combinations till the end of time, and yet somehow we churn out all these different chips every year, and they're always smaller, faster, better, right? So we have to have ways of doing that. AutoML is a lot of the same kind of thing. There is such an enormous design space. There's so many things we could possibly do to make our models better, to try and address things. And that's kind of what I want to talk a little bit about today is how can we look at AutoML for this tinyML future? So we're Qeexo, and that's really what I'm going to talk about. What is AutoML for tinyML? Qeexo is an interesting one because we've been around, Qeexo's been around for about 9 years, and we have models that have been tiny machine learning models for a lot of that time, kind of in the market since 2015, deployed on cell phones using time series sensor data, and they're on hundreds of millions of devices, kind of using them for these finger sense applications. If you haven't seen it, go stop by the booth, you can kind of see what it does. A lot of that technology that was kind of learned on how to extract that stuff, extract the interesting information, really build very, very small models, figure out how to extract the information very efficiently, very low latency, is kind of all encapsulated into, served as the basis for our AutoML tool that we just kind of generalized and turned into a product that we can now apply to any kind of sensor, in lots of these tinyML products. And so let's take a look at what that looks like and how we can do it without, kind of try and bring the power of those kinds of models and that kind of application to people who aren't necessarily embedded engineers or even machine learning engineers. So taking a, kind of a tradition, hey, what's the definition of what we're even talking about here, right? And I'll just ask Wikipedia, right? Automated machine learning is the process of automating the task of applying machine learning to real-world problems. Each of these tasks may be challenging, resulting in significant hurdles to using machine learning. AutoML aims to simplify these steps for non-experts, right? Like I said, I've been doing machine learning for like 5 or 6 years. Like everybody else, I took Andrew Ng's course on Coursera and, did some basic matrix math and was like, okay, I'm a machine learning engineer now. I'm good to go, right? I can do this. I can write Python. I'm good to go. And then, you start tweaking learning rates on, my neural networks, and wow, how do I set this number exactly? Okay, this is cool. Yeah, and so just like everything else in computer science, you start Googling it. You're like, oh yeah, you set it to 0.01. Awesome, yeah, that's cool. What happens when that doesn't work? And, and you start finding out all these kinds of things, and so what we find is there are these basic AutoML capabilities that people use for machine learning in all kinds of contexts, when it's big cloud, when it's vision, speech, anything, right? I'm doing hyperparameter optimizations, the parameters for the training process for the models. What are the model options for the size, the shape, the activations when we're talking about these neural network models, maybe for the size of trees or other kinds of models. If I'm doing model architecture search, maybe if it's neural network models, it's a CNN, it's a deep neural network, it's some other kind of model. Maybe it's not even a neural network. I want to look at tree-based models, or I want to look at SVMs or something else entirely. All that is part of what I consider traditional AutoML. And then we have, again, like we were already talking about, and like is obvious to all of us, we're in the tinyML world. What we're interested in is bringing sensor data into all this, right? How do we just feeding raw sensor data into these models? That's cool. It's really cool. It's really interesting from a machine learning perspective when these deep neural networks can learn how to interpret sensor data all by themselves, but it's kind of wasteful, right? It's awesome that they can learn how to do that, but it's burning a lot of bandwidth. It's burning a lot of processing power that we don't need when we can bring some domain knowledge to the problem. When we can do some signal processing, we can do some feature extraction to do that. But our customers might not know the right, even if they're domain experts, they understand the problem they're trying to solve. They might not be the signal processing experts that understand what's the right technique to pull that signal out of the noise or that signal out of the data. And so that might be a part of the AutoML search we can work on. Some models might need that feature extraction. Other models might want some feature extraction and some raw data, and we can combine all those things together, and they're going to impact the model performance and model selection kind of differently. And so you need to treat it all as part of the whole AutoML process, right? But all of that expands the dimensionality. It gives us more things to search across and more things to have to look at. And so you want to have it in a big common flow. Things that all work together. I'm not doing them all independently, because if I've decided on what features am I going to extract, how am I going to process my data, and then I start looking at how do I train my models, or which models am I going to use, well then I might have already made some suboptimal decisions. So I want to treat them all together. And so with Qeexo AutoML, that's typically what we look at. So at the top, you might have a traditional flow where you kind of bring all your data in, and in a manual process, you might go through data cleaning, pre-processing, feature extraction, select your models, do hyperparameter optimization, validate the model, convert it to C, compile it, build something, flash the binary to hardware. We try and package that all into an easy-to-use tool called Qeexo AutoML to just make it relatively simple to use, no-code kind of environment. And I'll show you a little bit of that, but let's talk a little bit more about some of the more AutoML-specific concerns, more of the tinyML-specific concerns that we have to worry about, right? So we also have to worry about not just what type of models best solve our problem in terms of giving us the best accuracy, but we now have a multi-objective optimization problem. We don't want to just optimize for one objective. We don't want to just make the best accuracy or make the best F1 score or whatever our objective is for how we measure the performance of our model, or minimizing the, but we also need to minimize latency or minimize power or minimize the size of the binary that we're going to run, or all of those things, or find the Pareto trade-off curve and kind of give our user some options, right? And maximize accuracy, maximize our F1 score, something like that. We also have to think about the kinds of constraints our hardware might have, that our processors on the tinyML hardware might not support all the capabilities of our desktop computers. Probably don't have a GPU. That's starting to change. More and more of them, sometimes we might, but we might not have a floating point unit. We might have limited memory. And so we have techniques like model pruning, quantization, hardware-aware optimization that can allow the model to run well on the target hardware. But most of the time, those techniques still kind of have some assumptions around, a traditional von Neumann compute architecture. I've got CPU and memory. I can run whatever kind of code that I can get a C. I can write C code or C++, that kind of lowest common denominator representation that I can go run. So any kind of feature processing I can come up with, I can run on there, which is good, and that's, a lot of times that can work, but lots of times, more and more, we're getting machine and neural network specialized chips that are being developed and productized. So they will even have more customized tool chains to go from some kind of standard representation, maybe open neural network exchange formats or other standard representations, to an output that's ready to configure the hardware. Right? And so we got to go from, and so it might go from neural network accelerators like ARM's Ethos-U that would take a TensorFlow Lite Micro plus a Vela compiler to create the right byte stream to get it ready to run. Or you can have something like S2 Microelectronics Machine Learning Core. Right? Machine Learning Core is effectively a hardware implemented decision tree. Right? This is not a general purpose processor in any sense of the word. Right? It's machine learning, for sure. It's a decision tree, and it's reconfigurable because it's a configurable decision tree. And there's software that can run it. But you have to consider all those things, and like the size of the decision trees you can use, what are your different capacities in there, while you're doing all the rest of your tool chain. So the full AutoML solutions have to be aware of those hardware capabilities and limitations when they're making all the other AutoML decisions earlier. Which model types and sizes work best is going to be different depending on the target hardware. So let's try and make that a little bit real. So we're going to use a very simple little example. This is a ST-Win board. We're just going to use the accelerometer and gyroscope, and we're going to do the wrist raise to talk. We're going to pretend we're taking little memos on my wrist-borne device. That's maybe a little bit clunky for a watch, but it's a dev board, so that's okay, right? Probably not going to wear it around. And here I'm not going for my production model. I'm just curious, right? I want to use the tool to see, is this a viable application? Can I very easily go through a prototype flow? Can I collect a little bit of data and see, at a lightweight way, can I build a model that's going to work? Is it viable? Is it useful? And what's it going to cost me in terms of execution, performance, things like that? So I just collect 6-ish minutes of data, some data where I'm raising to talk, that's kind of the positive case, and some background data, it's sitting around typing, stretching my arms, background stuff like that. And we'll go through and use AutoML to find the best model. We'll try 2 different use cases. First, we'll use the MCU. It's an ARM Cortex-M4 to kind of see, okay, if I use a general purpose compute, what models, what do they look like, how well do they do? And then we'll try using the really low power machine learning core and see what it looks like. Because the whole idea here is if we can keep the whole system sleeping, except when we raise to wake, we can save a lot more power. So just a couple screenshots. We'll start a new project, give it a name. We're just going to do classification. Tell it the hardware so that it knows what those hardware constraints are, what kind of processor we're going to use. Define the classes, give it the data we're going to use. Just tell it, pick the sensors, pick the feature, do it for me. If you want to manually select, if you want to do all that kind of stuff, of course you can. But the whole idea here, we're in AutoML talk, so we're going to do it automatically. And then tell it, just go ahead and try all the different kinds of models. And here we're really focused on trying a lot of classical machine learning models. So a bunch of tree-based models, ensemble kind of models, some support vector machine, SVM models, even some Bayesian kinds of models, even the logistic regression model in there. Throw it all in there because if we do some good feature extraction, lots of times we can find a really simple model that, and even a decision tree, but implemented in software rather than hardware, that can be really, really small and really, really compact and still do a pretty good job. And so it'll kind of pretty quickly, since it's not a large amount of data, it just took a couple of minutes to go through and train all those models, compile them, actually flashed all of them to the device so it could measure the on-device latency for all of them and kind of get some basic numbers on what was the training accuracy, what was the test accuracy. I didn't collect a lot of data. It overfit a little bit. Where it's a room full of machine learning engineers mostly, no one should be surprised. And so I just highlighted two in there, like a decision tree where, what did I get? 117 bytes. That's tinyML, right? Nobody's excited by that? Okay. So gradient boosting machines, like 3.8 kilobytes. So that's our goal here, is to really try and shoot for some really small models running at millisecond, less than millisecond kind of latencies. We can then flash and do some live testing, all of that, no code, just kind of be able to very quickly prototype and see how well it works. All of them kind of working really well and accurately as I was testing it and stuff like that. So that's cool. It worked. And those were just using kind of the feature extraction, all the signal processing stuff that we have built into the tool automatically. It's kind of built on a lot of our experience. It just goes and we have lots of different signal processing chains. It goes and evaluates all the ones we have built in, picks the ones that work the best, does it for you in the background. What I wanted to look at then next was how do we really leverage the unique hardware? And this is, like I said, I have that kind of hardware background, and that's what kind of gets me excited, is how can we kind of use that, that machine learning core to its best potential. And one of the unique features it has is beyond the hardware implemented decision tree, there are hardware implemented signal filters. So there's bandpass filters and low pass filters, high pass filters built into it. And you can configure those so that basically the output signals from the gyroscope and accelerometers run through those filters and can be hardware automatically featureized with a couple of features and then feed directly into that decision tree. Again, all at hardware, extremely low power. There's a blog post up there that kind of goes through some of the details, but it's running at microamps when it's just on that, running that MLC core. It's about 40x as power efficient as running with the full MCU. And so, obviously, if you're running at microamps, you get that, months on battery power kind of a thing. And so, with that decision tree, what we're able to do is using the data to drive, looking at the data to see, okay, where should the filters be? Where should we put those low-pass filters, band-pass filters, high-pass filters for your kinds of data? Help the user automatically get those filters configured. The user can obviously do it themselves. If they've got that expertise and want to do it, that's great. But it's AutoML. Let's see if we can do it for them. And so that was a feature we added last fall. Driven by the training data, the filter could automatically adapt to the activities being detected. And that really improves the performance of the model a lot. It gives you a much better result and much lower power. So for those, if we just did kind of a very naive manual configuration of the filters and the features just using the MLC chip, so not using the full MCU, the test performance was pretty bad, kind of flip a coin kind of a thing with the decision tree. If you do the automatic filter, it gets closer to 90%. It does pretty well. Here you'll see it kind of running live, and there it's been flashed. The MLC's been configured. And it's just kind of talking back across the USB to show you what the inference result is. So every time I kind of raise, I'm doing other stuff. It's keeping the MCU in sleep mode, or that's the output of the machine learning model. And then as I raise, it says, oh, it's in wake mode. Go ahead and wake up again. And we go on to the next thing. So that's my talk. I talked a little too fast. Good. I'll give you a little time back. But overall, what I wanted, kind of all I'm trying to say, as I've tried to say it, is, it's a really exciting field to me because I think there's so much potential here, but there's also so much complexity. I mean, that's what all of us have talked about, is that there's so much power in being able to do machine learning on these edge devices. As many have pointed out, there's also a lot of complexity to it. There's a lot of hard things about it. And the more things that we can do to dissolve those barriers to entry, to make it easier for people who are not embedded engineers, who are not machine learning engineers, and basically who are not the people in this room to understand that it's possible to build machine learning models that can run on these tiny devices and have intelligent devices be everywhere, is going to just enable so much really cool technology in the future. And so I'm looking forward to all of us working together to make that happen. So thank you.
Thank you, Elias. Perfectly on time, even earlier, 30 seconds. So time for question, please, to Elias.
Hi, Venkat. I have a question for both Jan and yourself. Putting you back on the spot. So this is really cool to have, but what I'm thinking about is how to explore architectures that are, so you say you generate C code, but you assume the architecture is fixed. What if we have a RISC-V with a coprocessor? How can I bring that into the picture? And where I can change what the hardware is.
Yeah, so I will say right now in Qeexo, we support defined lists of hardware. And so we support a couple of Arduino boards, a couple different ARM chips, and a couple of ST boards. And yeah, so we're not at that point yet of also trying to do the hardware search. I've seen and I've talked to professors at universities who have tried to do co-design between the two. That's really hard. I don't have anything more useful to say than that.
Yeah, sorry for hijacking this.
Please.
I mean, for us, we have a benchmark application. It's code you run it on the device and it has a latency number that you derive performance sure. So it's not 100% accurate, but it's decent enough.
So maybe what would be useful is if it gives us hotspots, then you can push that into the hardware, right?
Yeah, how do you say?
Okay, sounds good. Thank you.
Other questions? Maybe I have one. You were showing in one slide the deployability. There were different machine learning models with the model size and the footprint and so on. What about the RAM consumption?
So the size we show here is the size it's going to take in, is the flash size, and I think we don't take a lot more RAM. It's pretty much the size it's going to take on the device in RAM.
Okay.
And
so it means that it dominates.
Yeah.
It dominates the deployability.
Yeah.
Okay. Thank you. And maybe I have another one, if
Sure.
you allow.
Yeah.
What can you tell us about more about your experience in interfacing the embedded developer community? What are the lessons that you learned in interfacing them in your experience? If you have any lesson to share.
I think the hardest part is, I think something that I've heard a couple times the last couple of days, right, and even earlier today, is the ML development community is used to not having constraints as far as hardware goes, right? And so that's kind of, or when they do have constraints, it's oh, okay, that just means I have to figure out how to partition this workload across another 1,000 servers, or not a absolute kind of a thing. And so I think I think it's going to be a world of bringing some, it's going to be a job of bringing some hardware awareness to the world, which kind of, compilers people learned a long time ago. But, bringing that awareness of hardware and awareness of, real constraints on capacity and things like that, and kind of how to make those trade-offs and stuff like that, I think is, learning and communication is what it always ends up being, where we'll go from here.
Okay. Thank you so much.
Thank you.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Syntiant. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickatech, Latent AI, NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. And gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Grovity, Hymix, HOTG, Imagimob, ITMIS, Lattice, Nota, OmniML, PixArt, Plumerai, Qeexo, Rachner, Rixen, SAP, StreamAnalyze, Texil, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.